All right, hello everyone, welcome back. Today we're going to move on to our next flight lesson. We're going to be covering the ancillary controls, and the main focus will be range and endurance for today. So some of the ancillary controls, we're going to focus on the mixture control, the carb heat for carbureted airplanes, and then we'll talk about what is flight for range and what is flight for endurance. Your reference is the Flight Training Manual, exercise 3 and 10. The goal of this lesson is to teach you about the carb heat and the mixture, as well as any ancillary controls, and then also learn how to fly the aircraft for maximum range and maximum endurance, because you could encounter some situations where you'd want to configure in this way to help get to your destination or save some time. The purpose of the ancillary controls is really going to improve your skills as a pilot, let you fly more fuel efficient, save fuel, save money. Range and endurance does have real world application, such as low fuel or holding for weather. So this lesson is going to focus on some specific scenarios that you're going to find yourself possibly setting up. It's going to build really on the attitudes and movements once again, and straight and level flight for sure. If you have any questions, please list them down below. Some background knowledge for this lesson. If you want to pause the video and answer these questions, we'll start with number one. How do we slow down while maintaining our current altitude or reducing our airspeed? We've already done this. You reduce your power, slightly pitch up, and then trim. Power attitude trim. And to accelerate, you're going to add power, pitch down, and then retrim the airplane. Straight and level flight is maintaining a constant heading and a constant altitude. We have a 4-quadrant scan with a proper lookout. And how do we fly a straight track with wind? We'd have to apply, to track a road, for example, we would have to apply a wind correction angle into the wind. All right, so as for today, range is going to cover the greatest distance per unit of fuel consumed. So this is going to be the most fuel efficient way we can fly. Endurance is going to be flying for the most amount of time per unit of fuel consumed. So in endurance, you don't care about how far you go. You could stay in the exact same position. You only care about how long you're flying for. Next, we have ancillary controls, which are controls that provide the necessary support to primary controls for safe airplane operation. The mixture control. So on the right here, we do have a column of air from sea level and the top of the atmosphere. You can see that the air becomes less dense as we climb. And this is the whole purpose of the mixture control. So we need to compensate for the fuel as we have less air. So when we climb up, we have less air, we need less fuel. And that's the mixture control is going to allow you to reduce your fuel, and this is going to maintain your fuel-air ratio. So you're looking for about a 14-to-1 particles of air to 1 particle of fuel. If we leave the mixture full rich, you're going to be just burning excess fuel, and it's going to cost you more money. So the mixture control is the red knob located right beside the throttle. When it is all the way in, it is full rich. When it is all the way out, it is full lean, called idle cutoff. So that's the idle cutoff position. In the air, you can do fine mixture controls by turning it either counterclockwise for lean or clockwise for rich. So some different characteristics of a rich mixture compared to a lean mixture. When the mixture is rich, you may not develop rated power. So this would be if you're flooding the engine, you're starting to bog it down, The engine may run unevenly. It's going to really affect the temperature. A rich mixture is going to run cooler. We're wasting fuel. There's excess fuel being burnt. You could have spark plug fouling or carbon deposits on your spark plug, and you're going to reduce the overall range of the airplane. Now, if the mixture control is too lean, the power is going to be lost. If this is found when we're shutting down the engine, we pull it full idle cutoff, and the engine quits. Now, you could also have the engine to run rough or vibration, and this would be caused by pre-ignition. If the engine was too hot, your fuel air mixture is going to combust before desired. You may cause the engine to run very hot, especially on a warm weather day. You have to monitor your engine temperature, and you can run rich to help control that temperature. So now we're going to go over leaning out the mixture control. Two different methods. Method number one, we can be 50 degrees on the rich of our peak exhaust gas temperature. This method is found in the POH, and it uses this chart essentially. So we have 4 different lines on this chart. Starting from the top, there's the exhaust gas temperature, the cylinder head temperature, your power, and your fuel economy is the specific fuel consumption. So starting from the right is full rich, left is lean. So we always start from full rich, and as we lean it, you can see that your exhaust gas temperature is increasing. Your cylinder head temperature is also increasing before they both begin to decrease. The percent power is slowly increasing and then a fairly significant arc to decreasing as you get too lean. And your specific fuel consumption is mostly just decreasing until it flattens out. If we look at this chart, we have the best economy range and we have max power range. We always set it to our max power range in order to produce the most amount of power in the engine without, which is the 50 degrees rich of peak, somewhere around there. The reason we avoid the best economy range is although these engines are fuel injected, there is still quite a bit of tolerance from cylinder to cylinder on our fuel air ratio. So you can see the percent power curve becomes very steep towards the lean. So you're not going to be perfectly in the middle. You're going to have some cylinders way down in the bottom. You could have some up on the top, and that different power from each cylinder can develop a vibration and cause damage to the engine. So it's not recommended that you operate on best economy range. Instead, we lean out the mixture, we watch this EGT temperature rise to where it peaks, and then once we peaks, we go rich, which is going to bring us back down 50 degrees, and if we follow down, that's going to be your peak power. So this graph just helps explain that. You're going to be burning less fuel than at full rich, which is good, and we're not going to be harming the engine running it too lean or in some of the cylinders. Now, method number 2 works on a fixed pitch propeller, and all you're going to do is lean the mixture until you're at the peak RPM, and then as you lean it and it starts to decrease, once that decrease is perceivable, you'll want to go back rich, and that's going to bring you back up to the peak power. So that would be the peak RPM is our peak power. So if you can set that mixture to the highest RPM setting you can get, that's also a quick method of finding that. So the mixture review, why do we lean the mixture? It's to maintain the proper fuel air ratio as we climb and descend. The methods for leaning the mixture, we could go the rich of EGT or the peak power. And now not every airplane is 50 degrees rich of peak EGT. You'll have to refer to the POH for the recommended value there. All right, next we have carburetor icing. So carburetor icing is most common on warm, humid days, and it can occur from anywhere from about -13 to +38. So what happens on a warm, humid day, the air is warm, so it can hold lots of moisture, and it's humid, so that means there is lots of moisture present in the air. As the air goes through the carburetor venturi, the temperature inside the venturi is going to be well below 0 degrees, even if it's plus 15 outside. There's a large pressure drop, there's a large temperature drop, and that's going to cause the moisture that's in the air to freeze on the walls of the venturi and on the butterfly valve. So you're going to start to get ice buildup. If you allow this to continue, that ice is going to block your carburetor and the engine's going to quit. So to prevent this, we use carburetor heat. So it takes hot, unfiltered air from around the exhaust, and it redirects it into the carburetor, and it's going to melt that ice. Here's a picture of the carburetor heat. Generally, it's located beside your throttle. And once you pull that carb heat hot, remember it's unfiltered air. So generally, we do not use it on the ground because we don't want to be bringing unfiltered air into the engine. A couple other things to remember are hot air is less dense, so it's going to be a richer mixture, and we're going to lose some power. So full heat is going to cause a power loss. If the engine starts to run very rough, and it sounds like it's gonna quit, or you think it might quit, it is important to leave the carb heat on, because what's happening is there's carb ice present, it's melting, and now you have water going through your engine. If you turn it off, it's going to sound a lot better, but that ice is going to continue to build, and it's going to get worse and worse and worse, and it's going to get harder to melt out. So then in the future, when you pull it hot again, you could have an engine failure just from the water, and then you're not going to be able to clear it out. So if it's you turn it on, the engine's rough, you want to leave it on until that roughness goes away, and it should all melt, and then you'll get your power back. Alrighty, so now we'll talk about range and endurance. So starting with range, range is achieved when you're flying at an angle of attack that has the lowest amount of drag. So we have the most amount of lift and the least amount of drag. If we're looking at our chart here, we have our two red lines of parasite drag and induced drag, which combined together gives us our total drag. So the very bottom of the blue line is where the L over D max is found. So this is the area where we have the least amount of drag. If you look at our x-axis, the velocity, you can see as we decrease our velocity from cruise, the total drag is going to decrease until this point. And then as we decrease, the induced drag is increasing rapidly. So we have an increase in total drag. So in order to find range for the airplane, two different ways. We can look at the POH, go to our range profile chart, find our altitude, go to the desired percent power. We could read down bottom and get the range. And then to determine your percent power, you're going to have to look at your cruise performance chart, go to the same altitude of, if we say 8,000 feet, we'll look at the 8,000 feet. We need to determine if we're 20 degrees below standard or 20 degrees above. And then under the percent brake horsepower of, we'll say 65%, that would give you an RPM setting at 2,500 feet. So if you're at 8,000 feet, 20 degrees below standard, for 65% horsepower, you're going to set it the RPM of 2,500. So once you do that, you're going to lean out the mixture using one of the two methods, and that'll be set up for maximum range or close to it. If you want to get a little more accurate with it, you could use this experimental method, which is establishing straight and level flight at a high power, a cruise power setting, and you're going to note the airspeed. You're going to reduce 100 knots, maintain altitude, and note the airspeed. And you're just going to keep on doing this until you find a trend you're watching in the airspeed. You'll notice from 24 to 23, we've lost 5 knots, and we lose another 5, then we lose another 5, and then we lose 10 knots. Then if we reduce it again, we're gonna start to lose more, and it might not be exact. It could be 4, it could be 7. But what's happening if we go back to our chart? We're starting here at a high total drag, and as we reduce the power, we lose 5 knots for that power reduction. But the drag has also decreased, so that's not going to cause any effect on the airspeed, we'll say. But as you come back, we're losing 5 knots, losing 5 knots, losing 5 knots. And then once we're past the bottom, we'll reduce that 100 RPM. So we lose 5 knots for the reduction of power. But now the drag has increased. So that's going to slow us down even more. And that's where that increased reduction in airspeed comes from. So the power setting prior to the large drop is where we're looking to set the power for best range. Very important. Always lean the mixture once you've set that power setting. Lots of different factors that affect our range. Obviously the fuel, the more fuel, the further we can go. The angle of attack is going to affect the range. We want to be at L over D max or minimum drag. The airspeed, same thing. The aircraft weight, the heavier you are, we're going to have reduced range because we need more lift and therefore more drag. Center of gravity, if we have a rear center of gravity in the weight and balance, that's going to increase our range because we're going to have reduced drag on our elevator. The altitude, the higher we are, the more fuel efficient the engine is. Climbing, is it practical to climb up because you do burn lots of fuel in the climb? A headwind is going to decrease your range because we have a reduced ground speed, and a tailwind would increase it. The angle of attack, we want to be minimum drag, L over D max, and here's our experimental method for determining range. All right, next we'll look at flight for endurance. We have a separate chart for that. Flight for endurance is achieved when we're flying at the lowest power setting, able to maintain altitude. So we don't care about the airspeed. All we care about is the lowest power setting where we can still maintain altitude. You can look at the POH and find use the same method. There's an endurance profile chart. You can look at your percent power, look at your fuel endurance on the bottom, and then we'll look at the cruise performance chart to determine that power setting in RPM. The experimental method for endurance is starting with straight and level flight and just determining if you can maintain altitude. If the answer is yes, reduce 100 RPM. You'll have to pitch up to maintain altitude. Can you maintain level flight? Yes. We'll keep on doing this until eventually it's going to come to a point where you're going to reduce the power and you're going to pitch up and you're going to hear the stall horn going off. We do not want to stall the airplane. So you could lower the nose at this point. And the last altitude, we're able to maintain, the last power setting, we're able to maintain altitude would be the power setting for endurance. Once we have the power setting set, in this case 1900, we're going to lean out the mixture using one of the two methods. Some of the factors affecting endurance, obviously our fuel. The more fuel, the longer we can fly. The altitude, the lower the better. So sea level, because we can produce more lift at a higher density air. And we don't care about the drag because we don't care how far we're going. So we're going to have more lift and we're also going to have more drag. But the lift is, in this scenario, we don't care about the drag slowing us down because we're going to be staying in the same area. Flaps are going to decrease endurance because the flaps are going to, once again, increase the lift but they're going to increase drag to a point where you're going to have to add power to maintain your altitude. And as soon as you're adding power, you're no longer at the minimum power setting to maintain altitude there. Turbulence is going to decrease it because as you're getting bounced around, you're going to be correcting most likely with a little bit of power, as we won't be able to climb with the bare minimum power setting. We're going to lean out the mixture. That'll increase it. And a headwind or tailwind isn't going to change it at all because we don't care about how far we're going or how fast our ground speed is. Okay, review questions for today. The mixture is controlling our fuel-air ratio. It becomes more rich with carb heat on because the air is less dense. It's hot air. How do you set up the experimental method to determine range? What determines when we are flying at best range? The L over D max, or also the minimum drag. How do you set up the experimental for endurance? It's going to be lowest power setting. And what determines when we're flying at the best endurance on the graph? Minimum power required. Safety items today, keeping a really good lookout. Don't focus on your instruments. We don't want to become fixated watching the RPM and the altitude and our heading. So keep a good lookout outside. Confirming who's in control. I have control, you have control. And we don't want to run the engine lean of peak for an extended period of time. So when we're adjusting that mixture, we'll really pay attention to our EGT. So today we've covered some of the ancillary controls, flight for range and endurance. We're going to go up and we're going to practice the experimental methods for each, get you used to leaning out the mixture up in the air. Any questions, please leave them below. And the next lesson we're going to cover is slow flight.